Okay, we ready to begin? Let's see. Today I'm going to show you a little bit of programming and logic. I did a little bit last time. Before we jump into that, I just want to take a few of the slides out of the presentations. The presentations that I've posted for you are just generic presentations that came actually with a different textbook. So I only take a few slides out of each because sitting here and talking about what we're going to do doesn't really give you a lot of benefit. I'd rather sit down and do it in Logic so you can see it. I mean, it's easier to understand the context. But just for information, I've mentioned this a little bit, but the memory in Allen Bradley PLCs at least is typically organized this way. It's organized into files so that you've got file 0 is associated with the outputs, file 1 is associated with inputs, file 2 is the status file, then you've got the bits file. And remember, the bits file is the file I showed you guys last time, I think it was, where you can store information. It's basically just blank data memory for you to use. There's a timers file, a counter, there's a control file, an integer file, and this is another data file where you can store information. There's a file that's reserved, and then network, and there's a particular map. Every PLC is a little bit different. Okay, so it depends, even PLCs within the same manufacturer will be a little bit different. So you have to learn the syntax of the particular PLC that you're dealing with. Now there are typically files beyond this. Typically there's at least up to file number 255. Not surprisingly, most things in a PLC are based on integers or multiples of 2. Okay? So if you think about it, 256 is what, 2 to the 8th power? Right? So 255 is 2 to the 8th power less 1. Anyway, the files beyond file 9 are typically files that you can set up to be whatever you want. If you need more timers, you can make another timers file. If you need more memory, you can declare it, define it, and use it essentially as another integer or bit file, whatever you need. Now the distinction between the bits and the integers file, in my mind, is not really clear because both to me are just data. Both are a bunch of bits that I can use, but typically to keep your code clean, what you'll do is you'll put whole words of data into the integers file. If you just need a single bit, you'll use bits out of the bit file. But you can use words of data out of the bit file and bits out of the integers file. It's just to make your program more difficult for someone else to understand. Okay? So how do we address all of this stuff? Well, let's start by looking at input and output addressing. There's another slide that I think is especially useful. It's this one. Now, once again, from PLC to PLC, the way that you talk about a particular input or a particular output varies. Okay, but typically, what you'll do, your first item says which you're talking about, inputs or outputs. Okay, or essentially what file you want to talk about, because B is used for bits, N is used for integers, I is used for inputs, O are used for outputs. Okay, so here we're talking about a particular input to the PLC. This delimiter here, the separator, is something that tells you that what comes next is essentially a word. It's a whole bunch of data. Okay, so this is word 1, or it can be a slot number depending on the particular syntax. And then the slash tells you that what comes next is a bit. So this colon tells you that the thing following is a word, the slash tells you that the thing following is a bit of that word. Okay? So this is input 1, bit 2. This is output word 2, bit 11. Okay? And we'll talk about other addresses because you have to address timers, counters, registers, and other things. But I'll show you those in context rather than trying to expect you to remember a bunch of addressing for things that you don't really see any use for. Okay? Let's see now, there's a little bit more information in this slide. If you're trying to follow along the slides, this is 2-PLC hardware components. And I just wanted to show you that even within the same manufacturer, the way that you address the inputs and outputs varies a little bit. So here we've got the file type, O is output, 1 is input, and there's other addresses besides those. File number. Now in Logix Pro and in RS Logix, this is a duplicate, okay? It's something that is, for the most part, it's redundant. Okay, now, when that changes is if you define a file above file 9 as being an input or an output file, then you would need to say I, and then whatever the file number is. For example, I10, you could make an input file, or I11 could be an input file. Okay, you'd have to address it that way. because then the two are not redundant. You have another file besides file 0 that's talking about an output, or another file other than file 1 that is an inputs file. Okay? Anyway, then the next delimiter here, now here it says it's a file delimiter, but usually most people look at this as a separation that tells you that what follows is a rack number, a slot number, a word essentially of data. Okay? Well, in this case, I'm sorry, that's not right. In this particular PLC, this is a rack number and this is a group. So this is more the word and that's more the particular rack. Then there's a bit delimiter that says what follows the bit, and then there's a particular bit address or terminal number. Okay, so each PLC is a little bit different. If you look at SLC 500 instead of the PLC 5, notice what we got back, let's see, back there, I showed them to you there to the side, you can't see them, but that rack I had up here are all PLC 5. If you look at an SLC 500, which is also a very common PLC, then you notice there's something slightly different. There's a dot here, and that dot indicates that what follows is a sub-element. So the first number is the element, the next is a sub-element. Everything else is very similar. You got a file number, here a file type, a bit number after the slash. It's very similar, but it's slightly different. So you have to know exactly what the PLC expects. And if you go to another manufacturer, like I did for my own system, I bought a lot of automation. What's that?
Automation Direct.
Yeah, it's an automation direct. Click Coyo, though, is the name of it. If you buy that, then you have to learn the syntax for how you address inputs and outputs. And the general idea is that you need to know whether you're talking about an input or an output or something else. And for addressing, you need to know what word and what bit. Those are the big three things you need to know in order to get a PLC to talk to its inputs and outputs. Okay. So next thing I'm going to do is go into Logix Pro. And we're going to start working on the door simulator. Now, actually, before we get into that, actually we started last time. Before we continue in this, do you have any questions from the homework? Because there is a homework set that's due, what, next class, I think? Any questions on that homework set? I can bring it up on Blackboard.
It's not a homework question, but I need a CD.
You need a CD?
Yeah.
Okay. Someone was going to return their CD to me today. I got one, but there was another person.
I think this got one.
Okay, thank you.
Is that enough?
If you've got the CD, please make sure that at our break or after class you show it to me, and I'm going to record in Blackboard that you give, that you've got the CD and you return the one that I gave you. Okay, so any questions on the homework? Yes.
I can't remember which number this when you're asking us to what would be the address for like this input module A, B, C, D.
Okay. Why don't I bring it up? Talk about it, and everyone knows what we're doing. Let's see. Here we go. Homework 1. What are we talking about? This. Okay. Number the following input or output modules using the octal method. Use I for input and O, not 0 for output. All right, so if this is input A, the very first input, how would you number it? Well, these are just problems taken from your textbook, and it's a very generic numbering system that your textbook uses. But essentially, the answer to that one, this is all pretty straightforward. It's like permanent equals you, it can't be. It's coming off. It's the top of the race. Anyway, that first one, let's see. What do we got? Input module is 0. So it would be I0 slash 0. Okay, so I:0 slash 0 would be the very first input. The next one would be I:0 slash 1, I:0 slash 2, and so on. So it's a very simple problem. That's how I would number them. And the reason that this stays the same is because the module number is module 0. But since it's an input module, you have to use I, and each bit would have a different number. Now, when they say octal, it just so happens we end up with 0, 1, 2, 3, 4, 5, 6, 7. So you can't really tell whether it's octal or decimal. Number the following input-output modules using the octal method use the same instructions. So this is input module 1. The only thing that would be different here is that it would be module 1. The idea is that the most important parts are what file you want to talk about, what word in that file, and what bit. Everything else is a variation on that. Anything else? Now, there's no reason that you shouldn't get 100% on all of your homeworks, okay? Because you can ask me any questions you want, and I will answer. The purpose of the homework is for you to, now, do me a favor, don't come in here and ask me every single question and just fill them in. That's not going to help you in one. It's a waste of class time to do it. But I am willing to go over any homework problem you talk to. Anything else? Well, then let's work on the garage door. Last time we worked on the garage door, we got to the point where the motor would move up and down, and rather than reinventing the wheel, I guess I may as well go back and download the examples. While I'm at it, I will show you where I post all of this stuff. You go to Logix Pro in-class examples on the main Blackboard page. That will take you to a directory. And since I've got so much stuff in here, I've made a folder for fall of 2015. So all of this semester stuff should be in this folder. Okay, that doesn't mean you can't look at the other stuff. You're welcome to look at anything else. Most of what I do is the same from year to year. So you're welcome to look at all these other files if you like. But just to try and keep things a little more organized, I created a folder. And the program we ended with last time was door3.rsl. So I will open that up. We'll play with it. Now, if you remember, last time we talked, I had added a little bit to this. I guess I forgot to save it because we had set it up. No, there it is. We got motor up and motor down, not true. That way it cannot, you can't burn up the motor, basically. You can't hit open while it's closing and back. And if you hit close while it's already closed or open while it's already open, it won't try and open and close and so on. Yes, sir.
We can't get into the fall 2015 budget.
Can't? Well, let's see if I can figure out why. Edit settings. No locks. All comments private. There's no tracking, alignment. I'm sorry, I don't see a setting for changing. Owner created by.
You have to click the link under the.
What's that?
Like it'll say the Logix Pro in-class examples, and then it'll say it again in blue under it.
Oh, okay, so what you're saying is you can't even get into this directory, is that what you're saying, Mr. Leslie? Okay, so the suggestion is that you have to click here, you can't click here.
No, we didn't get there, but when you click fall 2015, it comes up with an error.
Yeah, so when you click this folder, it still won't open it? Well, I'm not sure what to do to make it work, so just to solve the problem quickly, I'm going to, let's see, make a new content folder. And it will point. Let's see. Maybe I've got the wrong to it. File. Yeah, here we go. Okay, browse content collection. And we want Logix Pro in-class examples in the fall 2015. But I think I grabbed it off. Yeah, I think I should. I still got it wrong. Somehow I want a folder, not an item, and I don't remember how I created that. Content folder. There's a content folder. Page content folder. Yet I don't have the option to add the folder. at the bottom of the page, do you have this? There we go. Move that up where it makes sense. Sorry, I didn't realize you guys couldn't access everything under a folder once I gave you permission to that folder. I'll give you access to it. Thank you for telling me that that was a problem. Now, does it work? Okay, so where were we? Oh yeah, I opened the program. So now we want to make this work better. Notice when we hit open, the door starts opening. We have no way to stop it. Even if I hit open or if I hit close again, it doesn't stop. It just keeps moving. It might be nice if the stop button worked. Okay, so how can I make the stop button work? Well, essentially, what I need to do is make the stop button interrupt the seal-in circuit, right? It has to clear this bit. So if I insert a set of context here that requires that the stop button be made, then when the stop button is not made, then it will clear the motor. Now, let me change the screen resolution. I'm sorry, I forgot to do that.
Which file are you using?
I'm sorry?
Which door program are you using?
The door simulator. If you go under simulations,
Which of the files that you uploaded?
oh, door 3.
Okay.
I don't have enough resolution to put both all of the door system and the program on the screen, but I'll refer to the program. So I'm going to add a set of context. Now, let me give you a hint. This stop button normally passes power. So do I want to add, in other words, it's a normally closed switch. Do I want to add an open set of contacts or a closed set of contacts? Open. All right? Because the examine if open, let's see, let me go back. The examine if open contacts won't be made until whatever's connected to it doesn't pass power. But this will always pass power. So what I want instead is the examine if closed contacts. Okay, so I'm going to drag it down here, drag another one down here. And just drag the address of the stop button over to those contacts. So this is the stop button. And Logix Pro, just like RS Logix, automatically renames or adds that comment to all addresses or all instructions of reference address. Okay? Now, think through this with me. The stop button is on input 1/2. It's on bit 2 of word 1. And since the button itself passes power, then that means if I look in memory at that input, that bit will be on, or the PLC is running. Since that bit is on, and this instruction looks at that address, at the address that the button's connected to, it's going to find a 1 there, and that's going to pass power. When the button is active, in other words, when the button is being pressed, the switch will no longer pass power. That will put a 0 into address 1/2, which means that this set of contacts will open up, cut that off, which will break the seal. Okay, so the stop button will stop the motor from moving up or down, because I put an instruction on both fronts. So let's download it, run, see if it works. All right. Open, stop, close, stop. It does work. Good. Okay. Now, did you notice over here on this PLC, this is made to look like an SLC file. Did you notice there's inputs here and outputs here? What does that represent? Well, the H suggests that we were talking in hexadecimal. We're talking in hexadecimal numbers here. So the inputs right now are 0, 0, 0, 6. Let's see if we can decipher that and figure out what it means. Okay, so what is the number C? Notice I didn't say the letter C, because in hexadecimal, we're using A through F as numbers. So the number C is what number in just decimal to start off with? 12. Was it? 12. Right, because you got A is 10, B is 11, C is 12. Okay. So 12 is the base 10 number, C is the base 16 number. What would C be? Citizens Band Radio, but what would C be in binary.
1, 1, 0, 0.
Right, because this is the 8s, the 4s, the 2s, and the 1's place, so 8 plus 4 is 12. Okay, good. All right, so there's the number in base 2. Now, what do you think that means? Well, what it means is that the inputs have bit 0 off, bit 1 off, bit 2 on, and bit 3 on. Does that make sense? All the higher order bits, all the more significant bits, all the other inputs are off. Let me show you where we can find this and show you that this is true. If we go to the data table by clicking the hammer and wrench and go to the, what is that, the inputs file, then you'll notice on the inputs file, which is all on word 1, on word 1, sure enough, bit 3 and bit 2 are on. Now, if we change this from binary display to hexadecimal display, what do you think is going to be displayed on this row? 0C. Okay? Because in binary, this number is a bunch of zeros, 1, 1, 0, 0, but in hexadecimal, it's 0, 0, 0, 0. Okay? So it's exactly what we see right here. If we change the inputs a little bit, if we make the door close so that this switch is made, then the inputs will change. In fact, input 4 will turn on because this limit switch will go true. Okay, so what is input bit 4? Well, this is bit 0, bit 1, bit 2, bit 3. So it would be in the next nibble, there would be a 1 that would come on. Okay. When that happens, what will this number change to?
1C.
1C, exactly. Because notice it's easy to map this to a single, well, let's do it this way. It's easy to map this binary number to a single hexadecimal digit. This will map to its own hexadecimal digit, which will be a 1, because that's the 1's place. Okay? So let's try it and see. So we'll close the door. Of course, our data table disappears. Sure enough, that came on, and we'll click hex, and goes to 1C. And that's exactly what's displayed over here. Any questions on that? This is all pretty straightforward once you start to get the idea of what binary and hexadecimal are, how to transfer back and forth between the two, and how each of the inputs and outputs are wired up to a particular memory location. Okay? Now, let's do another thing. We've got the open, the close, and the stop buttons working, and we're not burning up the motor anymore, but it would be nice if the ajar, open, and shut lamps would work. Okay? So let's make those function. In fact, we like the open lamp to be on solid when the door is open. When the door is opening, we would like for the open light to flash. Okay? When the door is ajar, plenty of jokes in there, corny jokes that I won't forgo. Hear enough of my corny jokes as we go along. You know, when the door is ajar, and in other words, halfway between or somewhere between open and closed, and it's not moving, we want the ajar lamp to, let's see, if open is solid, and when it's ajar and moving, we want the ajar lamp to flash. If we stop the door, we'd like the ajar lamp to be solid. Okay? Notice right now I'm deciding how I want it to work. And then the shut lamp would be similar. So I'd like to incorporate the lamps to indicate to the user the door's position. I mean, in this case, obviously, you can look at the door, he or she can look at the door and see what's really going on. But I'd like for these lamps to be indicator lamps. So let's program it. Now let me ask you a question. How many more rungs will I need in order to program 3 more outputs? Think about it. Each output in a PLC program requires a single rung at least. Okay. Typically, to figure out how many rungs you need, count the number of outputs, and that's the least number of how many you will need. Now sometimes you need less, sometimes you'll need more, most of the time you need more. But most of the time that's at least the number you need. So I've already got 2 rungs here because I have programmed 2 separate outputs, motor out or motor up and motor down. If I have 3 more lamps, then I will need 3 more rungs. So I'm going to just simply add 3 more rungs from the very beginning. 1, 2, 3 rungs. Now we'll put 3 output contacts on those rungs. I'm going to program the ajar lamp. I'm going to program the open lamp. I'm going to program the shut lamp. Now, let me ask you a question. If I were to download this program to the PLC right now and run it, what would happen? They'd all be on? They'd all be on. They would all simply be on because there are no conditions leading up to these lamps being on. That's not what I want. I want to have certain conditions for when the lamp is on and when it flashes. Let's program the lamps being on first, and we'll worry about making them flash a little bit later. Okay? So what are the conditions for the ajar lamp being on? What determines when that lamp should be on solid?
It's open.
It's open, right? When it's somewhere between the open and the closed. In other words, when this limit switch is made, when it's passing power, and when this one is not passing power, then the ajar lamp should either be lit or it should be flashing. One of the two, right? Like I said, we'll worry about flashing later. So generally the condition for a jar being on is input 4 not true, input 3 true. Okay. That's an AND condition. I want both of those things to be true before the ajar lamp comes on. Okay, one will be on, one will be off. Since both of these are normally open switches, I will have to use opposite contacts. In fact, I will want input 4 to be not made, right? It's a normally open switch, so when the door clears it, it will not be passing power. So there will be a 0 on bit 4. So that's the address I need to pass over here because I want to invert it. When there's a 0 in this address, input 4, I will want to invert that so that it's 1 and it can pass power to the ajar lamp. So the upper limit switch address will go here, lower limit switch address will go there. Those are the conditions needed for the ajar lamp. How about the open lamp? When will the open lamp be on?
The motor's going up. When the low limit switch is.
We have to be, okay, good point. We have to be kind of careful. We like to avoid using outputs as inputs if we can. I know we've already done that. We've done it here, we've done it here. This is for sealing, this is to cross the two. But if I can avoid using an output from the very beginning, it will make my programming a little cleaner and a little easier to understand, and I won't introduce problems. Now, as an experienced PLC programmer, if you do that, that's fine. But as a beginning PLC programmer, try to avoid using outputs as conditions for other outputs, okay? So let's be careful about that. What did you suggest?
When the lower limit switch is open.
Okay. I think the open lamp should be on when the door is all the way open.
Oh, yeah, that's what
Right, so it's not just the lower limit switch I care about, it's more the upper limit switch that I care about. So when this upper limit switch is not passing power, the door is all the way open. Okay? So let me use the upper limit switch as a condition. I think that's what you meant. When the switch is not passing power, that means it's open, it's in its normal state, and so I want to invert it. So I'll take an inverse set of contacts, and I can never remember which one's examiner open and examiner closed. I just remember what they mean. Okay. So I'm going to take a set of contacts like that, but I'm going to use this address for the open lamp. So what this will do is when the upper limit switch is not made, I will have a 0 on bit 3. That 0 will be inverted to a 1, and the open lamp will come on. That's really the only condition for the open lamp being on, is that upper limit switch. On the other hand, the only condition for the shut lamp is what?
the lower limit switch is on.
Exactly. If we've got a 1 on input 4, then shut lamp should be on. So let's program that as well. And thank you guys for speaking up. I know it can be difficult in the class, but I'd like this class to be more conversation than it is just me talking. Okay? I like that when that happens. So please feel free to speak up. All right, let's download this, run it, and see what happens. Well, that seems to work all right. The door's closed, and the shut lamp is on. We hit open, the ajar lamp comes on, and it finally opens the open lamp. So that works fairly well. Now, I'd like to modify it a little bit so that when the door is in the process of opening, then the open lamp would flash. Okay? Now, how can we make something flash? How can we make a lamp flash? Well, we need some time-based thing. I don't want to get into timers yet. I want to show you a trick that all PLCs have. Now, I don't know if I told you guys, but I admit it, I'm a real geek. Back in high school, I thought it would be fun one summer, I think I told you this too, learn how to program an assembly language so I could program a Tetris clone. And that was my summer. I had a blast. Everybody else was having what they called fun, and I was having what I called fun.
So you could program a what, a Tetris clone?
I'm sorry?
You can program what?
It was a clone of the game Tetris.
Okay.
Yeah, it was public domain quality, it wasn't very good. But I learned a lot about assembly language, and I learned a lot about bits and bytes and all that stuff. It served me well, even till now. Because anytime you deal with a small computer like an Arduino Uno or anything small like that, or any microcontroller, it's nice to understand binary and hexadecimal arrays. Anyway, so I learned a trick, because if you think about it, you guys have all played Tetris, right? Okay, there's what, 5, 7 blocks? There you got the square, you got the line, there's a left and a right L, and a left and a right S, which are always a pain to deal with, right? And then there's that T-shaped piece. So there's seven different pieces. Well, how do you decide what's coming next in the program? Well, you need some kind of random generator, right? Something to, at random, select one of those 7. So how do you do that? Well, sometimes you can generate a random number. There's functions to do that. But if you're in a low-level language like assembly language, it's really not an easy way to do it. So what do? Do you add a data table that has a bunch of pseudo-random numbers? So every time the user plays the game, they get the same sequence? That would be boring. Turns out that in most computers, in fact, even in my old Commodore 64, there's something called a free-running clock. It's a clock that counts clock cycles. So every time the CPU goes through another cycle, you'll increment the count in memory. Okay, there's just one memory address dedicated to that. So what I did, since it's a random, the amount of time it takes to go through the code and actually drop a block into position is a random number, depending on how much the user moves the block and makes it drop fast. All that's random. And so what I would do is when it was time to select another block, I would simply look at the clock, grab a few, all I needed, I think, was the lower, 3 bits, right? Because I've got to select one out of 7. And so with 3 bits, I can make a number up to 8, okay? Grab a number out of the clock, and then just use that to select which block would fall next. Well, in PLCs, there's also a free running clock. Let me show you. Right now our PLC is running. You go to the data table, and then you go to the status file. Address 2/4 is a really handy place to know about. Look what's going on here. There's a bunch of 1s and 0s turning on and off, and they're turning on and off so quickly, the actual Windows program here can't even keep up with this, and our eyes couldn't see it anyway. It's good. But if you look over here, you begin to notice that we're just counting in binary. This one's turning on and off. This one turns on and off alternately. Every 2 times this goes from 0 to 1 to 0. This one changes state. And this one changes state based on this one, and so on and so forth. It's just counting in binaries, okay? So every time the PLC goes through a clock cycle, it increments this bit, and this PLC is going through a lot of clock cycles per time. So what we might do is use one of these bits that seems to flash at a rate that looks good in an AND configuration so that we can make our lamps flash. Let me show you how that works. For example, this looks like a reasonable flash rate to me. So I'm going to look at address for bit 7 as maybe being a reasonable flash rate. Okay, so watch what happens. Go back into programming mode, and just to demonstrate how this works, I'm going to make the ajar lamp flash all the time. And I'm going to use status file, word for bit 7. I'm going to call this quick flash. Let's run this and see what happens. Download, run, open, stop. That's a fairly quick flash. In fact, it may be a little bit too fast for my liking. Okay, I can turn down the scan speed, but that's just playing with the clock rate of the PLC. So what I'm going to do is change this to bit 8, because bit 8 will flash at half the speed of bit 7. Download that, run it. That looks pretty decent. You see what I'm doing? All I'm doing is that I'm using a bit in memory that I know is turning on and off to kind of block this. So these conditions are true, but this blocks it every now and then so that the lamp flashes. It's a nice little trick to know that. If I needed a random number, I could go and take all 16 of those bits and generate a pretty decent random number. Okay? All right. Now, I don't really want the ajar lamp to flash all the time when the door is ajar. Sometimes I want it to be solid, sometimes I want it to flash. Now, at this point, since the flashing depends on whether or not the door is moving in all cases, right? Because sometimes I want the open lamp, the shut lamp, and the ajar lamp to flash. Since the flashing depends on whether or not the door is moving, I will have to reference the output contacts for the motor. Okay? Because I don't really have to, honestly. I could reference something else, but it's easiest to do it that way. So I'm going to break the rule that I told you, and I'm going to reference motor up and motor down as if they were inputs. And we have to think about it. We have to decide how we want this to work. And I don't remember exactly what I said, but I think I'd like the ajar lamp to flash probably when the door is ajar and it's moving. Does that make sense? Now that's going to be a little bit more complicated. So let's move on to the open lamp first. We'll take care of it first, right? So I'd like the open lamp to be solid when the door is open, but I would like it to flash when the door is opening. Does that make sense? So the conditions for the open lamp flashing are that the door is in motion upward, not downward, but upward. And what else? I think that's it, isn't it? You could say that some of the conditions are that it is not open yet. Okay, so this limit switch should not be, let's see, it should be made, or it shouldn't be cleared. So that could be one of your conditions, but I think that's redundant. Basically, when the door is moving up, I want the lamp to flash, so I'm going to OR around the upper limit switch. On this rung. I'm going to, this should be quick flash, I lost my comment. I'm going to add a set of contacts down here. It says when the motor is moving up, in other words, when output 2/0 is on, then I want a quick flash. Okay? See how this will work? Let me run it. Download it and run it so you can see. Okay. Let's ignore the ajar lamp for just a moment. I'm going to close the door. I'm going to hit open. See how the open lamp flashes while the door is in motion? If I stop it, the open lamp does not turn on. Because look, the motor is not moving up. Therefore, this flashing bit can't make the light flash. But if the motor is actually moving up, then this will be solid, and then this flashing can go through to the open lamp. Okay. On the other hand, if the door goes all the way up, then the upper limit switch will be made solid, and it won't matter whether this is flashing or not, because once again, the motor up will shut off, but this will keep the open lamp on consistently, constantly. Let's try it and see. So if we hit open and let it go all the way to the top, the open lamp should flash. Once the door reaches the top, the open lamp should stay on solid. So let's watch. It flashes, and it's on solid. So that works the way I want it to. Now, let me show you again in case you couldn't see. You weren't looking. I'm going to open the door again. It's flashing, it's the top, it's solid. Okay? Let's do the same thing for the shut lamp because it's similar. Basically, the shut lamp will have a very similar structure. We'll pour around the lower limit switch. We'll put in another set of contacts, but this one will reference the motor moving down. And we'll put in a set of contacts for the flashing bit. And now that one should work as well. And we'll run, close. It flashes while we're closing. And once it's closed, it stays on solid. So that works. I think the open and shut lamp work the way I want them to. Okay, now what happens if I hit open and then stop? Well, both the open and the shut lamp are off, which is the behavior I want. Now the ajar lamp, I think what I want to make it do is when the door is in motion but is ajar, that's when it should flash. I don't want it to flash all the time. If the door stops like it does right now, I want the ajar lamp to be on solid. So I'll have to pull this out. So I'm going to OR around this just like I did before. But the conditions for the ajar lamp flashing are slightly different. So let's OR around the upper and lower limit switch, which together indicate that the door is between the upper and lower limit. I'll put the flash down here. Now the way I'm going to do this is I have to add one more OR condition. If the motor is moving up, or the motor is moving down, then I would want this to flash. sense? If we are between the upper and lower limit, then these two will be true, and the jar lamp will be on solid. If the motor is moving up or the motor is moving down, then quick flash should happen and the jar lamp will flash. Okay? Do you see any problem with this? There is a problem here. Do you see the problem? What do you think is actually
true as well?
What's that?
First row will be
First will be true as well. Notice that this row is going to override this. Okay? So when I run this, you'll see what happens is that the jar lamp will always be on. It won't work quite like we had hoped. Let's run it, prove that. Open, close. If we stop it, the jar lamp never flashes. I want the jar lamp to flash. So how can we overcome this? There's another set of conditions for the light being on solid. We're missing those conditions because we've changed the definition of how we want the system to work. What are the conditions for the lamp being on solid? Not only does the door have to be between the limit switches, but something else has to be true. The motor should not be moving. Okay? So in this case, it's an and situation. Both motor up and motor down should not be true. Because if either one is true, then we don't want the lamp to be on solid. Okay? So let's download that, run it, and see what happens. Download, run, close. A jar lamp flashes while it's in between and moving. If we stop it, the jar lamp stays on solid. Now, I don't particularly like the way that the jar lamp flashes at the same rate as the open and shut. So what I'm going to do is use a different flash speed by simply choosing a different bit. I think I'll choose the faster flash. Okay. So this would be actually the slow flash. Bit 8, because bit 8 is above bit 7, bit 7 will be the fast flash. So download, run, open, close. You see that a jar is flashing at twice the rate of either open or shut. If I stop in between, the jar stays on. Let me slow it down for you a little bit so you can see it work. Close, jar is flashing, shut flashes at half the speed, open flashes half the speed, a jar lamp flashes at twice the speed. And sure enough, if I stop, the jar stays on. This is similar to what your author will have you do. If you look at homework 2, excuse me. Look at homework 2, which is not due this week, it's due next week. If you look at it, you'll see that I have you go into the student exercises and program something. Let me see, where is it? Let's see. Okay. Go to the student exercises on the CD, follow the instructions, and program the test, program and test, the door simulation exercise document in the program. Okay, let me show you where that is. You go into Logic Pro, and you go into Help, Student Exercises. It'll bring up a web page, which is actually local on the CD. There we go. And you can click the door simulation and student exercise 1 and 2. So there's instructions about how the thing should work. You can program it to make it work that way. Now I have tried to make my door simulation program similar to what they've asked for, but different enough, so that you won't be able to just copy mine. If you just copy my program, you're really hurting yourself. What I suggest you do, and I'll post this for you, but what I suggest you do when you get to that point, program, go into the student exercises, do your best to program it. And if you get stuck and you can't figure out how to program it, ask them for help. In lieu of that, if you're at home, look at my solution, see how I did it. And you'll probably be able to program. In my opinion, the quickest way to learn how to program in any language is by viewing sample code. See how it works, modify it, play with it, and you can learn then how to code. Okay? That will work fairly well here as well. I think that's the most efficient way. But let me help you with this as well. And before I forget, I better save this and post it to you guys. Any questions on that? How many of you have completely finished homework one? Okay, those of you that have finished it and you're comfortable with your answers, please move on to homework two. It'd be a good idea to get a little bit ahead. Those of you that have not finished it and need help, let me come around and help you. And for the next, I don't know, what do we have, 10 minutes till our break? The next 10 minutes or so, let me come around and kind of see where you're at and what you're doing, especially if you have any problems. Or if you haven't started the homework, please do start it. It is due next class. Well, technically it's due at 11:59 after next class. But I would like for you to get started. Okay? Those of you that are done and comfortable with it, start looking at homework two. There's a few things I haven't talked to you yet about on homework two, but we'll cover that when you come back. Okay? All right, so who needs help?
A question. Not what the